Hello, everyone. I'm Victor Bar, the Israeli Regional Coordinator of Asteroid Day Initiative, and I want to welcome you all to an Asteroid Day Israel event, Psyche Mission to a Metal Core, with Professor Benjamin Weiss. Currently, the asteroid space exploration is amazing, with all kinds of different missions. We have Hayabusa 2 that delivered a sample of asteroid Ryugu and is now headed to study another fast-rotating asteroid. OSIRIS-REx is en route to Earth with a sample from asteroid Bennu, and after that, it will study the most famous asteroid Apophis. Lucy is on its way to study the Trojan asteroids, and DART is about to impact not an asteroid, but an asteroid that is a moon of another asteroid. And Lycia Cube will photograph it all. Great times indeed. We have become experts in studying rocks and ice in space, but we have one thing missing in that puzzle: the study of all metallic asteroids that circle around in space. This kind of study will bring many scientific benefits to us, and today we're having one of the leading experts in the world on that subject. But first, a few words about Asteroid Day and our partners. Asteroid Day was founded 7 years ago, and Asteroid Day Israel joined shortly after. The main purpose of Asteroid Day is to raise the public awareness to asteroids, both as a threat to Earth's cities and population, but also as an exploration of scientific opportunity. And we at Asteroid Day Israel want to reach the Israelis and the Hebrew-speaking public for the same reason. Our speaker today has an amazing story to tell us about his mission, and I'm sure you will enjoy listening to him. You can ask questions by writing them in the chat, and I will present them to our speaker. But before introducing our speaker, I want to thank my partner and friend, Itai Leon, our gifted space graphics professional from Astrographics, for creating all the graphics material for this event. I hope you all saw the video he made. If not, go directly to Facebook to Asteroid Day Israel page and take a look. I want to welcome Hilai Shurun, the New Horizon Community Manager that helps me with the Zoom account and the coordination with ISA, and would like to say thank you to the former community manager, Adi Saada, for all the help in the past years, and also today. Also thanks to Bar Hayun for helping and publishing the event on ISA's website. And as always, I wish to thank Saulo Machado from Asteroid Day Global for always being there to help and always and in every request I make. And also great thanks to Colleen, Stuart, and Danica Remy for all the great work they're doing for Asteroid Day. Love you people. And now let us welcome our speaker, Professor Benjamin Weiss. He is the Deputy Principal Investigator and Magnetometry Investigation Lead for the Psyche Mission. He is a professor of planetary science of the Massachusetts Institute of Technology, or MIT. He conducts laboratory studies of extraterrestrial samples and in situ spacecraft exploration to understand the formation, evolution, and habitability of planetary bodies. Ben, welcome aboard. The Zoom is all yours.
Hi, thanks for having me. Really happy to be here. Hello, everybody. So today I'm going to tell you about the Psyche mission, which is NASA's next discovery mission, which will visit the metal asteroid 16 Psyche, metallic asteroid, shown here. I'm going to basically talk about two different things. I'm going to talk about where we're going, which is the asteroid Psyche. And then I'm going to talk about our mission, the spacecraft, which is the Psyche spacecraft. They basically share the same name. Okay, so let's first talk a little bit about the asteroid. Okay, so we are going to this asteroid 16 Psyche, which is the 16th asteroid to be discovered. It's a 226 kilometer on average diameter body, and it orbits in the main belt with a semi-major axis of about 3 astronomical units, 3 Earth-Sun distances. And we think it's the largest metal-rich asteroid in the solar system. And question is, why do we think this thing is so metal rich? Well, it seems to be super dense. And the way we know that like any kind of density for any body, is we have determined from ground-based observations its size and its mass. You put those together, you get a density, of course. Okay, so let's talk about the size. It's a little bit bigger than, not quite as long as Israel is, but about the size of Israel in terms of its surface area. And its mass, so that's very well determined, the size. Its mass, the most important way we've determined is by watching how small asteroids, as they pass by Psyche, their orbits are perturbed by its gravity. And from those perturbations, it's like maybe a couple dozen such observations of different small asteroids, we've been able to determine the gravity field and therefore the mass of the body. And this is actual simulation of all known asteroids since at least as of 2018. So Psyche is in the main belt in the yellow region there. So from this, we've determined to very high precision, like a few percent, that its mass is about 1/300,000th of that of the Earth. So it's a small body. Okay, so we put that together, 226 kilometer sort of mean diameter, and I think it's about 10 to the 19 kilograms or so. And given the uncertainties on those measurements, we estimate now from ground-based data that Psyche's density is, Psyche's volume is somewhere between 1/3, say almost 2/3 metal. So, and that's based on the fact that its density, we think somewhere between 3,400 kilograms per cubic meter and 4,100 kilograms per cubic meter. So, you know, just for a typical, you know, rock that you'd pick up on the Earth might be about 3,000. So even the lower end of this range is more dense than any typical rock you'd find on Earth and the vast majority of known meteorites. And for comparison, the Earth, whose core is about half of its radius, it's about 16 volume% metal. So this is a very metal-rich body. Okay, so the interesting thing about this mission is that when we first proposed Psyche, or start thinking about proposing Psyche, which is way back in the, like after 2010, somewhere between 2010 2014, we knew Psyche was even then a dense, probably metal-rich body, and that it was likely the largest known metal-rich asteroid in the solar system. So there's also a metal-rich asteroid in the main belt known as Cleopatra here. Some of you may be familiar with. It's like the dumbbell-shaped asteroid. And there's a whole, you know, there's dozens of so-called X-type or M-type asteroids that are inferred to have high density, of which Psyche seems to be the largest member and is in many ways representative of this population of bodies. What we've come to realize is that Psyche is more than just the largest metal asteroid. It's in terms of composition, it's representative of a very broad range of bodies that we now know to exist throughout the galaxy. So for example, Mercury, which has a similar range of iron abundance as I just quoted for Psyche, it's basically a core, like 80% of its radius is metal, when there's a little bit of rock pasted on the top, about 20% of the outer radius. And even more interestingly, perhaps, we now know over the last few years that there's a diversity of exoplanets, planets around other stars, whose density, it ranges from Psyche up to even almost that of pure metal. The most recent such discovered body that garnered a lot of interest is this object GJ367b. Its radius is about 80% of the Earth, so it's huge, and it orbits very close to its star, so it's why it's often depicted to have these molten regions. And then there are bodies that are even super Earth size, larger than Earth, that range up to pure metal, depending on the uncertainties. So we can now see that Psyche is not an exotica, a weird beast that we just want to see what it's like because we've never been to a metal place. Of course, we do want to see what a metal world is like, but it's even more importantly, it's representative of a range of bodies that we now know to exist, all the way from the smallest near-Earth asteroids. There's a near-Earth asteroid that's only 3 kilometers in size. It's about the same density as Psyche, all the way up to things bigger than the Earth. We'd like to understand how these so-called iron worlds form. This informs our overall science goals. So first, we want to understand Psyche as an asteroid, in particular, representative of a range of small bodies that are metal rich, that are the residual population of an early population of bodies that we sometimes call planetesimals, which served as the building blocks of the planet. So most asteroids that exist in the early solar system, which when we call them planetesimals, are now part of planets, which they created to form. So we'd like to understand how the metal-rich end member of that population that formed the planets formed, because it actually affects how we think planets formed and evolved. Secondly, Psyche as potentially a core of a planet. So we think one of the ways that Psyche could have formed is that it was a regular planet in terms of its density and rock to iron ratio, but then a impact of another body stripped off its outer layer and left it with an almost naked metallic core, leaving us the opportunity, of course, therefore, to study the core of a planet. So we're never going to go to the Earth's core in our lifetimes. The temperature is hotter than the surface of the sun. The pressure is 1,000,000 times the surface pressure of the Earth. But here we have Psyche, potentially waiting for us with an exposed core for study. So that's Psyche as a core. And then the third thing is, what is it like? What is a metal world like? What we've been to worlds made out of rock, of course, like the Earth, Mars, Mercury. But what about bodies that are made of, and we've been to bodies made of ice, like comets and the moons of the outer solar system, planets. But what about a world that's made out of metal? What does an impact crater look like on a world made of metal? How does a volcano work on a world made out of metal? What does tectonics, like the cracking and motion of the crust under pressure forces, look like on a metal world? We can study that by looking at Psyche. All right, so we have a number of objectives that flow down from that. Only one I'm going to talk about today, which is kind of our defining and central objective, which is in fact Psyche a core? Did it form from the metal-rich interior of a planetary body? We think many bodies, once they get beyond a certain size, or if they form early enough, they basically undergo large-scale melting. And in doing so, heavy stuff will sink to the center and light stuff will float to the surface, and you'll naturally form a metallic core, since iron is the most cosmically abundant heavy element in the universe, or at least in the galaxy. So we think bodies, when they form early and melt, naturally form these cores. And in fact, the Earth has one. All the planets have these metallic cores, even if we can't visit them. So perhaps Psyche formed in the same way, and then some process, like an impact, stripped off that rock and left us the naked core we see today. The other possibility is that it's formed somehow with a composition that does not match the bulk solar system composition. So the Earth and most of the planets, we think their bulk composition matches the sun and what most of the parent materials of the solar system contain, which are also close in composition to what we see in the nearby galaxy. You would maybe somehow there was a selective process where only the iron-rich materials formed a primordial body. Maybe there was some rock thrown in there, and then it never underwent any large-scale melting, so it just formed primordially iron-rich. And so whatever we find out for Psyche also will apply to our understanding of all those other bodies I just mentioned, all the iron worlds that we now know exist. Okay, so how are we going to do this? I'm just going to walk you through our kind of logic and our approach, how we're going to try to solve this problem, whether it's a core or not. So this is how we imagine it could have formed a core. So imagine there was an early body in this 4.5 billion years ago. Because if it formed early enough, it would have had some isotopes in it, like 26 aluminum, which actually have short half-lives, undergo radioactive decay, would help heat the body and melt it, forming a molten interior that's made of iron, shown here in orange, with a rocky exterior shown in brown. Then if there was some impact of another body that shattered that, and then somehow Psyche could reaccrete from the metal-rich material, either maybe the impactor itself's material, or maybe the body that was hit. That molten material, if it's made out of iron predominantly, iron has a special material property, of course, that it can be electrically conducting. And electrically conducting fluids can generate magnetic fields because they can basically, the motion of the fluid as it undergoes its cooling process, which causes it to churn, like the material in your lava lamp. This churning of this liquid conducting metal can generate currents, which in turn generate a large-scale magnetic field shown here in purple. And in fact, this is exactly the way the Earth and Mercury generate their magnetic fields today, is the churning of their liquid metallic cores, which lead to current generation. So we can imagine the same thing could happen in an asteroid. In fact, we see lots of evidence for that in other asteroids. So if Psyche formed as a core and it was a molten core, it could churn and generate this magnetic field. And then as it cooled, it's a small body, the outside potentially could crystallize first where it's coldest, while the inside continued to churn. Maybe there even would be some eruptions at the surface like you see here. And what's important about that is that cooling crust of metal could then lock in a record of that magnetic field, which we call a dynamo, the purple, in the form of same kind of thing that you see on your refrigerator pneumatic, something we call remnant magnetization, which is basically the electrons within that metal. They're like little compass needles, and they can come aligned in that purple magnetic field, just like a compass needle can. And then even when the dynamo is gone, you can actually see after the body is frozen, those electrons remain aligned in the crust, just like a magnet keeps its magnetization. And then if we were to fly a spacecraft through that, as shown schematically here, we could look for evidence of this ancient magnetic field, now recorded as an echo in the form of this so-called remnant magnetization, these electrons aligned. Whereas if the body had never melted at all, it would have never generated that magnetic field, and it would not be magnetized. Okay, so here's just to go over this again. Imagine you had a body. It formed here as a metal world, had a molten interior shown in red with a solid metal exterior. That molten interior generated a little magnetic field here, like you see around a bar magnet, around the Earth's magnetic field, shown in these red lines. The electrons in that solid, cool outer layer, here schematically represented as little compass needles or arrows, they basically align with the background magnetic field. And then even today, you could detect the remnant magnetic field, the blue lines from those electrons, even though the magnetic field from the dynamo is long gone. Compare that to something that never melted, it remained unmagnetized, and it's unmagnetized today. So the presence of a magnetic field today, even though Psyche is long frozen, would provide powerful evidence that Psyche formed as the core of a body that underwent large-scale melting. So interestingly enough, although we've never detected the magnetic field of an asteroid, in the last couple of decades, we've come to realize that from laboratory studies of meteorites, samples of asteroids, that many asteroids, in fact, did generate magnetic fields in their churning metallic cores. And in particular, iron meteorites, meteorites made out of almost pure iron that we think came from Psyche-like bodies. We've now seen many of them have this magnetization, these aligned electrons, which provide evidence of an ancient magnetic field. Here's an example. It's a so-called 2E iron meteorite. That's just a random name for a bunch of iron meteorites that came from a body. We don't know where this body is, but we call it the 2E iron meteorite parent body. This particular meteorite is known as Miles. It was found in Miles. And if you look up really close, you see this mineral everywhere called camosite, which is basically an iron nickel mineral. But you also see these darker regions here, and they're kind of gray, and they're zoned in gradation. They have a lighter exterior and a darker interior. That material, that darker material, and particularly the light rim, is a different mineral called tetratenite. And we've learned how to read the record of that tetratenite by using magnetic studies, and in particular, using a synchrotron, this very powerful high resolution X-ray beam that's generated up in University of California, Berkeley, the so-called advanced light source. We can zoom into that tetratenite here. So you see the camosite boundary at the lower left, and then the tetratenite rim. And then there's another tetratenite region we call the cloudy zone, because it kind of looks cloudy. And what's cool about this new technique is we can actually image the alignment of those electrons. This is actually a magnetic map. The last one I just showed you was a reflected light image, a photograph. This is a high resolution map of the magnetization itself, of the electrons themselves being oriented. All right, so what's cool about that is we can actually use this to see that the rock is magnetized, that it formed in the presence of an ancient magnetic field. Okay, so we've now done this for 4 different groups of iron meteorites, which we think came from 4 different iron meteorite parent bodies, none of which we know where they exist. There's the so-called main group pallasites. These are spectacular mixtures of peridot, olivine, this iron silicate mineral, and metal. I'll show you a picture in a second. And we see that their body was magnetized, and that it must have had a huge core, something that kind of looks like Psyche, or we think we might look like Psyche. We've seen another iron meteorite group, looks like it had a smaller core, and was a naked metallic core that was like kind of resembling the picture we described for Psyche. It was like it crystallized from the outside in, was magnetized also, and generated a magnetic field in its center. Then we have another group of weirder iron meteorites that are kind of a mix of metal and rock that never fully melted, never fully formed a core. And this thing is not magnetized because it never did form such a core. And then finally, the 2E irons that I just showed you a second ago, they kind of look more like the Earth, like a core that's about half the size or so of the Earth with a rocky exterior. And they too generated a magnetic field. So you see, just from the 4 different iron meteorite groups and parent bodies that we've studied so far, you can see a huge diversity of different evolutions and structures. So this just goes to show you, we really have very little clue what iron asteroids look like in their interior. And that's not just interesting scientifically, of course, but also from the perspective that someone might mine them someday. So has actually practical implications. So you see a huge diversity of outcomes. Some bodies, most bodies that we've measured so far did generate a magnetic field, but not all of them. And that seems to correlate nicely to whether the body formed a core or not, because the 1AB irons never formed a core and they're not magnetized, et cetera, et cetera. Okay, I could talk about that all day, but let's just briefly look at the pallasites for a second. So here's an example of a pallasite. If you've never seen one of these meteorites, I strongly recommend you see if you can see one in a museum. They're a beautiful mixtures of metal and these gemstones, essentially. We think they form near the top of the core of their parent body. And we've now measured a bunch of pallasites. And what we can do with that high resolution synchrotron imaging is actually measure the strength of the ancient magnetic field that each meteorite experienced when it formed as a function of time after the body formed. And what's cool about this is that we can actually map in time the strength of this magnetic field generated by its interior. Some of these error bars are large, as you can see, for the later ones. But we see basically a field arise in the body about 100 million years after it formed. And that field strength, which is about 30 here at microtest, is about the same strength as the Earth's magnetic field today. The reason this is interesting is that we can see that there was first no dynamo, and then their dynamo turned on after the body melted and its core began to crystallize. And basically, we can see using how long this dynamo lasted, how long this magnetic field lasted, and how strong it got. We can learn a lot about the interior structure of the body. And that's where we've established that it was somewhere between 300 and 700 kilometers in radius or so, and had a density like Psyche. So the pallasite parent body, wherever it is, in many ways, it looks a lot like Psyche. Maybe it's a little bit bigger than Psyche, but almost certainly similar density and stuff. Actually, our dream is that Psyche is the pallasite parent body, because you can imagine how spectacular a body, if Psyche turns out to have cliffs of pallasite with those gem quality gems, like, glinting in the sun. Anyway, it seems unlikely, but it's fun to think about. Okay, so how are we going to get there? Here's the spacecraft. Here's it on the left without any solar panels shown. And here on the right is the full spacecraft. You can see that the bus, the central part, is a tiny fraction of the size of the whole body. It has these huge solar panels because its propulsion system is by electric propulsion. It doesn't use liquid or solid rocket fuel. It basically shoots out ionized xenon at high velocity out of its back end. There's 3 different instruments. There's an imager for taking images. There's a magnetometer for measuring the magnetic field. And there's a gamma ray and neutron spectrometer for measuring gamma rays and neutrons. And then there's also this fun technology demonstration, a deep space optical communications device, which basically will practice sending data to Earth by visible light, by lasers, rather than by radio waves, which is the way all previous spacecraft essentially have done. And that's how we're going to do as well, this big dish here, the radio. But if we can get that to work, it'll likely be an important payload element for future missions because the data rate is very high. Okay, so here is Psyche. It's basically complete, and it's actually at Cape Canaveral, waiting to be launched. And here it is right before we shipped it to Cape Canaveral a couple of months ago. Here it is at the Jet Propulsion Laboratory. Okay, so here was the nominal plan, which changed very, very recently. I'll get back to that in a second. Okay, so we'd start out at the Earth. We were supposed to launch in September 2022, and then fly by Mars to get a gravity assist that would throw us out to the asteroid belt. During that early period, the deep space optical communications main mission would go forward, where we'd be sending laser communication to the Earth. Then we expected to be captured at Psyche in 2026, and then stay there for the next 20 months or so with 4 different orbits at different altitudes, starting from orbit A at the highest altitude, then lowering down to orbit B, lowering down to orbit C, and then the closest orbit D there. Now, the planned end of operations was in 2027. Okay, so just last week, NASA put Psyche's launch on hold because the flight software, even though the spacecraft itself essentially is done, the flight software also built but hasn't been tested completely, and we just ran out of time to test that software. So right now we don't know exactly when we're going to launch. We're looking at opportunities in a year to 2 years from now, and we'll probably know a little bit more in a few months. So maybe we might end up getting there in 2029 instead of getting there in 2026. Okay, so this is the 4 orbits I just mentioned. You can see how big they are compared to the asteroid itself. The gray lines show you as we spiral from one orbit to another. You can see orbit D will actually change the inclination of the orbit almost 90 degrees, so we can map the surface of the body. All right, so just to end, I'm going to tell you a little bit how we're going to use these instruments, these 3 instruments, to test the objective of whether Psyche is the core of a body that underwent large-scale melting, or whether it's a primordial iron-rich body. So here is the magnetometer. So in addition to being the deputy principal investigator, I am the lead of the magnetometry investigation. So this is the instrument I've been focusing most of my time on. And you can see it's got a bunch of coils wrapped around a sphere for measuring the magnetic field. It's actually a flex gate magnetometer, for those of you familiar with that. And what we're going to do is measure the magnetic field around the body. And probably the most important indicator of a remnant magnetic field, that is an echo of an ancient magnetic field that's recorded as aligned electrons, is the strength of the field. So Psyche will be, like all bodies in the asteroid belt, immersed in so-called interplanetary magnetic field of the solar wind. This the plasma that the sun shoots out in all directions at hypervelocity. And at the asteroid belt, that's like 2 nanotesla or so. So if we see fields near the body much stronger than that, then we can infer that Psyche is in fact magnetized and formed as the core of a body. So this shows you a simulation of the asteroid in orbit of the spacecraft flying around the asteroid, here shown in the gray sphere, at the orbit D altitude. And these are just the X, Y, Z coordinates here. And you'll see the strength of the magnetic field that we measure as a function of time as the body rotates and the solar wind blows from the right toward the upper left along the negative X direction. This gray volume here is basically shows you the region where we see, for this particular magnetization strength, that the field is stronger than the solar wind. So you see there's this bubble around the body where the field is stronger than what would be predicted if the body was not magnetized. And you can see traces out that nice donut shape. And it turns out this magnetization that we're guessing for the body here is compatible with what we've measured from those iron meteorites that I showed you earlier. So this will be how we get the map during orbit D. It goes on and on and on. And eventually we'll build a map up as a function of latitude and longitude. And you can see everywhere greater than the dark blue, we detected magnetization that indicates a magnetic field that indicates Psyche is magnetized. And like I said, the reason this is an important demonstration is this is basically would assume Psyche is like the 2E iron meteorite miles that I showed you earlier, for example. All right, so the next instrument is the gamma ray and neutron spectrometer. This is a two-part instrument. It measures gamma rays and also measures neutrons. I'm mainly going to focus on the neutron aspect of this, although there's a lot more to be said here. Just focusing on that, this is a kind of instrument for those who haven't heard of it before. You'd think if someone told you that they were going to do this, you'd say they're crazy. There's no way this is going to work. But it turns out this was conceived in the 60s, and it's now been flown on many different missions, from Moon to Mars, asteroids, Mercury, and it's worked beautifully. So the principle is very simple. You have cosmic rays. These are these high energy particles. They're mostly just nuclei and mainly just protons without any electrons around them that are produced, we think, around pulsars, supernova, things like that, from the galaxy around us. When they penetrate into the surface, because they have so much energy, they interact with the material on the surface, the atoms, and then that creates a cascade of neutrons that are knocked off from these the atoms that they interact with. And some of those, what we call fast neutrons, which are the high energy ones, can escape directly out of the surface to be measured by the neutron spectrometer. Some of them, on the other hand, actually bounce around and lose some of their energy as they interact with the material that they're passing through. And that can lower their energy to what we call the epithermal range, or even lower to the so-called thermal range. It is just lower energies. And we can measure all of these different neutrons and their energies using the instrument I just mentioned, and actually map the surface to some extent with it. So this is just to show you that this works. Here's some neutron spectrometry that's been done on the moon. So here's a picture of the moon, visual image. It's actually UV, but the visual image looks similar. You can see the famous mare, the lava plains, shown here in the middle, and then the highlands, which are the white rocky, material around them. So the mare, which because they're basalt, they're iron and titanium rich, and the highlands are iron and titanium poor. So more broadly speaking, the mare have larger abundances of elements with lots of protons and neutrons in their nucleus, whereas highlands have lower amounts of heavy elements. And it turns out the fast neutron flux tells you what the material's average atomic number is, the number of protons and neutrons in their nuclei. So it's a measure of this. And so if you, in fact, you make a map of the neutron flux, you see the high atomic number, the iron-rich material has lots of neutrons, and then the low atomic number has a small amount of neutrons. And that's what we're going to try to do on the moon, on Psyche. So this is another way we'll be able to see whether Psyche has got large iron metal regions. If we see large regions with lots of fast neutrons. It turns out also low abundances of thermal neutrons also would indicate iron-rich material. Okay, the last thing is the imager. And the imager will be taking essentially photographs, multicolor, what we call multispectral photographs. So this just shows you what we will measure as a function of wavelength, so visible light essentially. And then it has these different filters, 3, 6, 7, 8 filters located at the locations, the wavelengths shown by the diamond, where you can kind of measure essentially the color of the body. So iron, turns out, looks like a red material, looks red in an image. So it's got more reflectance at the higher wavelengths, whereas rock tends to not look like that, and it has kind of deep absorptions at the higher wavelength. So we'll be able to map out the metal, the rock, and the metal as a function of orientation too, position as well. And if we see, again, large regions of metal coincident with high fast neutron flux and strong magnetization, that would again indicate that Psyche is the core of a differentiated body. Whereas if we see a homogeneous composition somewhere between rock and iron, no magnetization and no fast neutron flux, that would indicate it's more like a primordial unmelted body. Okay, so let me just end. So the galaxy contains diverse metal-rich bodies ranging from asteroids all the way up to super-Earth exoplanets, and including a near-Earth asteroid that we might actually mine one day. The Psyche mission will be the first to orbit a metal-rich world. That's asteroid 16 Psyche. And we want to know whether it formed as the core of a melted body or it's primordial. And a core could be distinguished by its strong magnetic field and large regions of high fast neutron flux and red color. And with that, I'll just leave you with a video. You don't need to wait for this to finish. That just shows a simulation of the Psyche spacecraft as it approaches and orbits asteroid 16 Psyche. So thank you very much for your attention.
Thank you very much. Thank you very much, Ben. We have so many questions to. I hope we will be able to ask them all. Okay, so first of all, before we start the questions, I want to say something. We have among our audience a 12-year-old Hayden. He's a planetary defense ambassador, and he is very enthusiastic about asteroids. He's saying that during this mission, will you look at potential landing sites on Psyche for future missions, such as asteroid mining? Thank you for inspiring me, Hayden.
Thanks for your question. So our objectives do not include specifically looking for landing sites for future missions. I should say, by the way, it's actually conceivable that after orbit D, we will lower the spacecraft even further. I mean, it's even conceivable. There's by the way, the Palisade cliffs that we do a hard landing, although that's not in our current plan. But even though we look for landing sites, we make the data. There's two things that we will do that will enable that. So first of all, we're going to make it a map, and in particular, not just a geologic map, but we'll map the topography, which is going to be critical. Secondly, we will measure its gravity field to very high precision. Measuring the gravity field is essential for any spacecraft, any future spacecraft mission that would want to land on the asteroid. So we'll have a topographic map, we'll have a gravity field map, we'll have an image map, and those are the essential ingredients for determining where a spacecraft might land. And whether we or somebody else chooses to do this, there certainly will be the information available to make such an assessment. Maybe it should be you. The data will be publicly available very soon after we get it. So I expect that information will be available to do that. Thanks for the question.
Perfect. Now we have some questions about the laser communications. Tel Aviv University is making advancements in setting up a new 24-inch telescope capable of laser communications upon one of the building roofs. Will Psyche be able to contact this facility via its laser communications array, or is it intended to use only in space? And one more question: who is the supplier of this laser communication?
Right. Okay. So I am not an expert in this. I'll tell you what I know. As I said, the reason to do this, and I'm sure you know this already, but saying this for everybody else's sake, is that you can carry a much higher data rate with a laser. Now, why haven't we done it already? It's maybe the next question of some people, if that's the case. The central challenge of doing this is that you have to basically point that laser incredibly precisely so that you can actually see it, right? And that requires a high stability. So my understanding is that that there will be an observatory in the US that they will be communicating with. So I don't think that and they will be steering that laser so that it directly interacts with that specific observatory. So my understanding is the beam is smaller than the size of the Earth, but I could be wrong about that, which would mean that not everyone could choose to observe and look for that laser. It'll just be this specific observatory. Yeah, that's that. But there is more information about all of these different instruments and the spacecraft itself that will be coming out in the next year from a special issue of a journal called Space Science Reviews. We can learn more. There was another part to that question, right?
Yeah. Yeah, who is the supplier of the laser communication?
Oh, right, yes.
Yeah.
Exactly. It's built by the Jet Propulsion Laboratory at NASA's Jet Propulsion Laboratory.
I see. Okay, Roy wants to know any infrared spectrum signature of the asteroid to understand the various elements of the outer crust.
That she wants to know, do we already have that information now? Presumably, yeah. So yes, there is a very, I'm going to let Dor off into the room. We do have some spectral observations of Psyche, and it's not totally flat. So let me go back for a second. So you see here, this is not, if it was pure iron meteorite powder, then you'd basically say there's no evidence of anything but, it would just be a slope like this. In fact, we see a little bit of a dip around 900 nanometers, which lets us think that there's a little bit of low calcium pyroxene mixed in there, maybe a few percent or something like that is the current estimate, maybe 10%. So there seems to be a small amount of rock, at least a small amount of, like a few percent on the surface by surface area. And in particular, this mineral pyroxene, this iron, magnesium, silicon oxide, silicate. We also see that absorption feature at 900 nanometers changes as a function of when we look at the asteroid as it spins. There are also other maps that have come out of other material properties that show that the surface probably varies in its metal content and its maybe rock to metal ratio. So it's probably not a completely naked core, a metal core. There's probably some rock on the surface somewhere. We don't know the extent to what's covered by rock.
I see. Okay. Majd wants to know, is it possible to install a telescope on an asteroid to have it travel between the star systems?
Anything's possible. Of course, the main problem with traveling on an asteroid is that it doesn't have its own propulsion, right? You can put a telescope on there, but it's just going to keep going around the sun. And then you have to wonder, what's the advantage of putting it on an asteroid rather than just putting on a rocket, which has its own natural propulsion system?
Okay. Alon and Uri want to know, is it worthwhile extracting resources from asteroids and delivering them to Earth? I think they mean especially metals.
Right. So there is a lot of discussion about mining asteroids, which is what you're talking about. Probably the first wave of asteroid mining, which almost certainly will happen at some point, will be looking for water ice, probably not looking for metal, and using that as a resource for basically other spacecraft that have already in space. So you can imagine it's for fuel, using it for making rocket fuel. So a rocket wouldn't have to go down to the surface of the Earth. A spaceship wouldn't have to go down to the surface of the Earth and refuel. It could just go to an asteroid potentially and make fuel from the hydrogen that's available on the surface. But probably a later phase will be mining asteroids for, say, steel, in which case like iron, nickel in particular. Psyche probably won't be a target for mining for a very long time, if ever, because it's hundreds of millions of kilometers away from the Earth. But there is this asteroid 1987 DA3, I think it's called, and it comes within something like 30 million kilometers or so of the Earth, which still sounds like a long distance, and it is, but it's much closer than that Psyche. that near-Earth asteroid, people have thought about what it would take to mine that for metal, because we think it's about the same metal abundance as Psyche, maybe 50% metal, maybe even 60% metal by volume. If it is a metal world, the problem is the studies I've read so far right now, it's not economical, meaning, it's going to cost way more to get the metal out of there right now, given the lack of infrastructure, the lack of equipment and space to do this kind of mining operation. So it wouldn't, right now, it looks like it's not going to pay off, but it could in the future once there's more infrastructure, there's more support system that's been launched as part of other space efforts. So probably, not next 10 years, but maybe you could imagine in our lifetime, or certainly yours. I don't know how old you are.
Okay, Alon wants to know, it's a question related to the previous one. Is there an asteroid made of gold or of diamonds?
Pure? Well, Psyche and all these iron bodies I just showed you, they do have gold, and they do have platinum, and they have more than just iron for sure. But if they are like what we think they are based on the abundance of those metals on Earth, then it might be 1 out of a million of the volume, 1/1,000,000th of the volume would be those metals, gold and platinum, things like that. So that is a small number. However, Psyche weighs 10 million trillion kilograms.
Wow.
And if you take 10 million trillion kilograms and you multiply that divide it by a million, you still have a huge number. So there's a lot of gold and platinum up there, but it's just not, most of it's not made out of that.
Okay, so the next question is, it's like we have to ask it. Uri asks, will the next mission to study a metallic asteroid will be able to return a sample from it to Earth, and presumably a lot of gold in it?
So this one we're only going to orbit. If we're lucky, someday we can think of landing. We're not going to bring a sample back. There are plans to bring. Well, we just brought a sample back from a rocky asteroid called Ryugu. We've already brought a sample back from a previous rocky body named Itokawa. In a year or two, we're going to have a sample of another asteroid, and then there's a mission that's on its way. It's going to go to the moons of Mars, which might also be asteroids. We're not sure, to bring samples back from that. So if you think about this, it seems like sooner or later we're going to get an asteroid specific and to do that, and our mission won't do that.
Mm-hmm. I see. In a different subject, are the Janus twin spacecrafts are part of the Psyche mission, or they are just hitching a ride on the rocket?
They are hitching a ride on the rocket, so they're a totally separate, independent mission. And we have basically, all we've done is we got a big rocket, a Falcon, SpaceX Falcon Heavy rocket, and we have extra space in there. So NASA said, hey, anyone want to use this? You just design your mission to be able to fit in there, and you can use it. So that's the extent of cooperation we have between them, between Janus and Psyche. Okay,
I see. Another interesting question about the composition of Psyche. How do you know if the meteorites that were found in Campo del Cielo in Argentina came from Psyche?
Oh, we don't. In fact, we don't know of any known meteorites that come from Psyche. We haven't ruled that out either. There's some ideas. So Campo del Cielo, I'm trying to remind myself what type of iron meteorite that is. The nice thing about giving a talk on Zoom is you can actually look something up real time on the internet. So let me see if I can remind myself. Let's see, Cielo, yeah, there it is. Okay, so this is a yeah, I don't know what kind of meteorite this is. It does Wikipedia is not good enough to tell me what kind of. Yeah, I don't know this one by offhand particularly, but what I was going to say was you're right. That's the more important point, is that there are many, many iron meteorites. Okay, in fact, with something like 120 different asteroids that we have samples from in the form of meteorites. That, you know, they were randomly blasted off their asteroids by an impact, and then they wandered around space and landed on Earth by accident. And 80% of those, something like 90 of those bodies, are iron meteorite parent bodies. So most bodies that we have samples of, in fact, are iron bodies. So it's quite possible that one of those 90 different bodies that we have samples of, whether it's Campbell del Cielo's parent body or something else, might be from Psyche, but we don't know. We've never identified an asteroid that comes from a meteorite that's iron, unfortunately. Not yet, but actually that's something that the Psyche mission could potentially do. We might get enough specific information from orbiting Psyche that we could then go look in our own meteorites and say, oh, wow, that particular meteorite actually is from Psyche. And we didn't know that until we went and visited it to see what the body was like. So that's something that might come out of this, although we're not necessarily counting on it.
Okay, and we have one last question from Majd. He's asking about the operation of the spacecraft. How will the mission team operate the spacecraft around the asteroid? Is it completely autonomous? Do you have to upload the code? How does it work?
Yeah, it's a mixture. So one of the reasons we have these 4 orbits, A, B, C, D, if you remember where you go, is that we don't know Psyche's gravity field very well. So you need to know the gravity field well if you want to orbit very close, because the gravity field gets lumpier and lumpier the closer you get to the body. It's nice and smooth once you're out here at orbit A, but it gets really lumpy at orbit D. And so in order to be able to continue to orbit the body and not to crash into it or to basically fly away from it, essentially, we need to basically do these progressive lowering of the orbits from A to B to C to D, and we measure the gravity field in each one before proceeding to the next lower orbit. So that process of transferring from one orbit to another will definitely involve not automatic controls, but human controls. Other things, that are automatic, for example, the magnetometer, which will measure the magnetic field. When we launch, we're going to send a command that says turn on, and then we're never planning on turning it off ever again for the next 6 years or however long it's on. It'll just take data and send it to us. So that's an example of where it's automated. So it's a mixture of both automated and human commanded sequences.
I see. Okay, so our time is up, unfortunately, because I think we could ask you many more questions. You don't believe I have two pages filled with questions. So this topic is very, very interesting, and this was a brilliant talk. I enjoyed this talk very much, and I definitely welcome all of the listeners to view and listen to the recording. We'll publish it both on Asteroid Day Israel Facebook page and Asteroid Day Israel YouTube channel, along with other places. So I want to thank you again for joining us. Thank you very much, Benjamin, for this great talk. It was amazing. And happy Asteroid Day, everyone.
Happy Asteroid Day. Thank you.
Bye-bye.
Thank you very much.
Thank you.